All right, so here is section 2.2 defining the derivative, which again I talked about it in our lesson yesterday about as we were doing the process of the difference quotient with the limit, and we were getting our answers. I was telling you that as we found the instantaneous rate of change, we were finding in one stage was the derivative of the function. So that's what we're going to focus more on today. Is in a moment here is how to find the derivative of a function. But let's define first what the derivative is. The derivative is an expression that calculates the instantaneous rate of change, or the slope of the tangent line of a function at any given x value. In other words, it gives us the slope of the function at a point. So here on the left-hand side, we have the quadratic function f of x is equal to x squared. Over on the right-hand side, and we're going to talk about this notation here in a little bit. When we see f with a little apostrophe after it, we pronounce that as whoopsies. We don't pronounce it as whoopsies, but we pronounce it as f prime. Is what we say it as. Is what we is how we talk about it. So the f prime, or the derivative of our function, is 2x, and we're going to show you in about 5 minutes about how to get that derivative by a process. And so down below here is we have three different problems where they ask us to estimate or calculate what is the instantaneous rate of change when x is a certain value. So all we would do is we would just take our derivative function and say, okay, what is f prime of 1? Well, what is 2 times 1 is 2. So, with that in mind, when we look at our equation, let's see how neatly I can do this. When x is 1, so here's when x is 1, the slope at that point on that curve is 2. So that would be something like, hopefully, there, where we have a rise of 2 and a run of 1. And so at that point there, the slope is 2. Next one here says f prime of 2. Well, that would be just 2 times 2, which is 4. And again, if I was able to draw this neatly, and where we connect right there, and I draw that tangent line, what would happen is we would notice we would have a rise of 4 and a run of 1. So we would have a slope of 4. On the other side, if at f prime of negative 2 would be 2 times negative 2, which is negative 4. And again, that would mean that at this one location here, if we drew the tangent line, we would notice it would have a slope of down 4 over 1 is what it ended up happening. So, hard to freehand those lines in there, but that's basically what we're saying is taking place here. So in problem 1, it says if f prime of x is equal to 5 over x minus x. Again, we don't care about what the original function was. They asked us to find out what f prime of 2 is and then explain its meaning. So calculation-wise is pretty simple. We're just plugging it in and being careful. 5 over 2 minus 2. That's 5 over 2 minus 4 over 2, if I got common denominators and so forth, which is equal to 1/2. So the slope of the tangent line at x equals 2 is 1/2. That's one thing we can say there. We can also say that the instantaneous rate of change when x is 2 is 1/2 is what another thing we could say there. So if we want to write that down there, the instantaneous rate of change when x is equal to 2 is 1/2. Number 2 says if f of x represents how many meters you have run and x represents the number of minutes, describe what the incentives for the following things. So this is what we've been doing most of the math that we've done so far here, like in our course of schooling-wise of math. We're basically saying after, in this case, after 8 minutes, because they told us x represents minutes, so after 8 minutes, you ran 1,500 meters is what that interpretation would end up being in a sentence. Now, notice how we have the notation here, f prime of 3. So remember, f prime is the slope. It's the instantaneous rate of change. So in that standpoint, when I would talk about this, I would say when x equals 3 minutes, or at 3 minutes, if you want to say it that way, when x is equal to 3 minutes, the instantaneous rate of change is 161 meters per minute. And again, the instantaneous rate of change is a rate of change, so that means that we should be having some type of rate of change unit taking place here. So we would want to make sure we include that, hey, it's meters per minute. And the previous one, we want to make sure we put the units on at minutes, or at minutes, and the answer in meters, saying, hey, after this many minutes, you traveled this far. Here, my rate is my 161 meters per minute. So we were talking about the different notations out there with Newton and Leibniz and so forth. So Lagrange is another one of the mathematicians. Lagrange likes using more of a simpler process, is what Lagrange likes to use it when we do stuff. So what we typically see is we see the F apostrophe is what we see for the notation for a derivative. And if in some cases, if they don't use function notation, we may just see a Y apostrophe. Again, those things are pronounced as F prime and Y prime. We'll see as we progress through this unit, especially this chapter, this notation here with one apostrophe indicates that we have the first derivative is what we have. There is, as you add apostrophes, that indicates which derivative you're talking about. So if you see a Y with a double prime, as the way it's pronounced here, Y double prime, that is equal to the second derivative of a function. And again, we're not going to do that right off the bat here, but eventually in the next several lessons, we will eventually take multiple derivatives. At some stage with certain functions, sometimes it stops and you can't take the derivative of the function anymore. And in certain functions, the derivative is endless. You can keep taking it and you never come to an ending point in taking the derivative. But typically we mainly deal with the first, second, third derivative is throughout the whole this course. Sometimes we ask for the fourth derivative, but very rarely. And we'll talk about that later on in the chapter. The Leibniz notation, that's where we're actually using the D. We're using D. So we usually see like dy dx is what we see as the notation. And so what here we want to make a note of this because it helps with later chapters. This is, as we talk about it in a sentence, the way this stands for this notation, it says the derivative of y with respect to x. So as we take the derivative of the y equation, we're going to do it with respect to x, the variable that's in there. Again, and that's important because later on, as I mentioned in class yesterday, I mentioned about this when I did the Windex, when I was pouring the Windex into the bottle. We were talking about the change in the volume of the of Windex coming out of the bottle had a rate that it was changing with the change in volume with respect to time. And then how is the volume changing in the cylinder I was pouring it into, or maybe how is the change in radius with respect to time taking place, inside of that container. So we do want to be able to work with both sets of notations. Leibniz notation for second derivatives and so forth. It's a little bit more complicated look, and I'm not going to do it right here. We'll do it in the later lesson when it actually comes into play when we're asking to find more than just the first derivative of a function. The definition of derivative, this basically, and this is a key thing here that you're going to have to be able to maybe show on a free response question, a subpart, for you to find the derivative of a function using the definition of a function, and that involves using the limit process. So this limit gives us an expression, and here's what it looks like. It says the limit as h approaches 0 of f of x plus h minus f of x over h. And so again, we started using that in what we were doing a little bit in class yesterday. So and that we know that this basically is equal to, in a way, let's use Leibniz notation, f prime of x. So the derivative of the function f of x is equal to the limit as h approaches 0 of the difference quotient of our function. And so we're going to practice here in a moment how to go about doing this, showing all the work and showing all the steps. Again, it's long. It's easy to lose track of things, so be very careful. And I'm going to try to be very careful as I go through doing things by the definition of the derivative. So they say find the derivative. So my goal is to find out what is f prime of x. Well, I know that is equal to the limit as h approaches 0. So now what I'm supposed to do is take my original my function and put x plus h in for all the x's. So it's 2 times x plus h quantity squared minus 7 times x plus h plus 1. And then we're supposed to subtract the original function. So back off the original function. So parenthesis 2x squared minus 7x plus 1. I'm going to go ahead and move that second one over here, and I'm just going to white it out, is what I'm going to go through and do just to kind of get it out of there. So there's number 4 over there off to the side. All right, so now that is all over h. And now I need to start simplifying. So f prime of x equals the limit as h approaches 0 of 2 times x squared plus 2xh plus h squared. And then it is minus 7x minus 7h plus 1. Then negative 2x squared plus 7x minus 1. That's all over h. Again, very lengthy process here, f prime of x. The bigger the function, the more tedious it is to do by the definition, but we have to be able to do it. So I'm now going to distribute the 2 in there. So I have 2x squared plus 4xh plus 2h squared minus 7x minus 7h plus 1. Then I have minus 2x squared plus 7x minus 1, and that's all over h. Now I'm ready to cross out or combine like terms and so forth. So the 2x squareds cancel. A minus 7x and a 7x cancel. And a 1 and a negative 1 cancel. And I'm left with f prime of x equals the limit as h approaches 0 of what it looks like is 4xh plus 2h squared minus 7h over h. I can't apply the limit let, so we're going to go ahead and say f prime of x is equal to the limit as h approaches 0. I know I can factor out an h. To save room, I'm just going to go ahead and just take my pen and say this h in the denominator cancels out one of each of the h's that are in each of the part of the numerator. So this gives me f prime of x is equal to the limit as h approaches 0 of 4x plus 2h minus 7. And then now we can apply our limits. So f prime of x is equal to 4x minus 7, because it'd be 2 times 0, which is 0, so it'd just be 4x minus 7. So there is the derivative of my function. right, again, if you want to pause, rewind that, watch me go through it. I mean, again, it's doing it by the definition. You got to show all that parts there. I know it's tedious to keep going F prime, F prime, F prime, and writing the limit as H goes to 0, but we need to show all those steps there. All right, problem number 4 here. Problem number 4, they asked us to find the derivative of that function. All right, fair enough. So let's see. Let's see, F prime of X, or actually they're using the Leibniz notation there with a Y, so we can just instead just go through and actually write it as Y prime is equal to the limit as X approaches, or sorry, not X approaches, as H approaches 0 of, okay, so it's the original function, 1 over X plus H quantity squared minus 1 over X squared over H. All right, so Y prime is equal to L limit of H goes to 0 of, let's see, 1 over X squared plus 2XH plus H squared minus 1 over X squared. That's over H. And again, these are always the tricky ones. We need to get common denominators, which happens to be both things that are on top there. So I can rewrite this as Y prime is equal to the limit as H approaches 0 of 1 over X squared times X squared plus 2XH plus H squared minus 1 over X. Let's say now, what I forgot to do was multiply the top by X squared, because that's what I had to do. And then on the next fraction, I'm going to multiply the top by X squared and bottom by X squared plus 2XH plus H squared. On the bottom, we now have common denominators. And that's all over H. So Y prime is equal to the limit as H approaches 0. On top, I have X squared. And then I have minus, I get to change the sign here. I get to take this negative and distribute it to each of those things. So that would be a negative X squared minus 2XH minus H squared all over X squared times X squared plus 2XH plus H squared. So let's do some simplifying. On top, I can cross out the X squareds, and that's about it. So Y prime is equal. That's all over H. Almost forgot that guy. Now, technically, that H there can actually now be brought up to the numerator. So it can actually be brought up to the numerator, and that's because of the keep, change, flip, multiplied by the reciprocal thing taking place there. So the limit as H approaches 0 of negative 2XH minus H squared over H times X squared times X squared plus 2XH plus H squared. I see that the H out that I just moved up to the numerator, this H will cancel that H and one of those two H's. So Y prime is equal to the limit as H goes to 0 of negative 2X minus H over X squared times X squared plus 2XH plus H squared. Now I can apply my limit. So Y prime is equal to negative 2X minus 0 over X squared times X squared plus 2X times 0 plus 0 squared. And so that gives me negative 2X on top. On the bottom would be X squared times, that becomes 0, so X squared. So Y prime is equal to negative 2X over X to the 4th, and then we would simplify to be negative 2 over X cubed. And there is the derivative of the function. And again, we do that, so now if they tell us to evaluate it at an x value, now we can find the slope of the tangent line. We can find the instantaneous rate of change at that point. That leads us into the last part of the lesson, the equation of the tangent line. So the equation of the tangent line to the curve f of x at a certain point, let's say x is equal to a, can be represented in point slope form as follows. Y minus f of a equals f prime of a times x minus a. So that's what they're saying there is you can basically define the equation of the tangent line. We would basically have our x value or a value for x, whatever that numerical number is, do the equation, evaluate it at that number to find the f of a, and then we would take the derivative and plug in the a value to find the slope. So I'm going to walk you through that in the next couple problems on how we do that. So if we know h of 5 is -2, so that tells me that -2, 5 is, oops, sorry, Mr. Stevens almost made a boo-boo there. We know that if I put 5 into the function h, I get -2 for an answer. So there's my point. And the derivative, h prime of x, so the derivative they show me here is x cubed minus 2 over x, write an equation of the tangent line. So we want to fill in our point slope formula. This is what we want to do. Right now we know that it's y plus 2 equals something times x minus 5, because they tell us in the statement here, they tell us what point we're going through. Now I just got to find my slope at 5. So they gave me the derivative. So what is h prime of 5 is what I have to do numerically. So 5 cubed minus 2 over 5 would be 123 divided by 5. So 123 fifths. And again, typically you don't have to, in calculus, you don't have to simplify and get it in slope-intercept form. Usually all they would want us to do is actually bring the 2 across. And most answers we will see is y equals -2 plus 123 fifths times x minus 5. And that's typically how we will see most stuff on the AP exam written. They usually just ask you to keep it in point slope form in a way, but just get the constant with the y over to the other side is all they ask us to do. You don't have to worry about distributing from there and going from there. And I wouldn't bother, because that's what they have as a format of an answer that's down there for them to grade by. You distribute wrong and combine like terms wrong, now you can lose points later on a problem and so forth. So the graph f prime of x is showed on the right-hand side. If f of 2 is 7, write an equation of the line tangent to the graph at 2, 7. So we know we're going through the point 2, 7. So I can go ahead and fill that. Now here's where we got to be careful. They told us that this is the graph of the derivative graph. So on this standpoint, what we want to do is we want to figure out, okay, what is the y value when x is 2? So on the derivative graph, what is the y value when x is 2? So that is 3. So that tells us that f prime of 2 is 3. So our slope is 3 of our tangent line. So we can go y minus 7 equals 3 times x minus 2. So y equals 7 plus 3 times x minus 2. And that's where we get to stop. Again, one of the biggest tricky thing as we go through this course is sometimes they give us a graph like here, as I just draw on it just to say which one I'm talking about. Sometimes it's the graph of the derivative. Sometimes it's the regular graph of the function. Sometimes they give us the graph of the second derivative. And that's usually as far as they go with those with displaying graphs. So as we progress and we learn things, we'll go through it nice and slowly. Again, if you have any questions, just give me a shout.